So let's look at example 63. So I want you to integrate 1 over x squared plus 4x plus 8 dx. So if you remember from last time, I told you that integration is not easy because we don't have the product rule or we don't have the quotient rule for integration. The thing that we have in our hand now is the substitution rule. So our idea is we are trying to simplify this thing into something we know how to integrate. So if you recall what we have, so what we have is we have integrate of 1 over 1 plus x squared dx. This is arctan x plus c. Well, the form that we have is 1 over 1 plus x squared. But in the given problems, I have x squared plus 4x plus 8. So it is not an exact match now, but we can simplify it. So let's consider the function x squared plus 4x plus 8. Well, we need to simplify this thing to something that is easy enough to integrate. So first of all, I am going to complete the square. So I'm going to say that x squared plus 4x plus 8, this is equal to x squared plus 4x plus 4 and then plus 4. The reason why I do this, I'm trying to complete the square. So this is going to be x plus 2 square plus 4. Right? This is the idea how we complete the square. So complete the square. We're going to use this technique a lot when we learn integration technique after midterm, but to show you the idea. So this example is a good one. So after that, well, I am going to say that my integration is x squared plus 4x plus 8 dx. So after I simplify it, so it's 1 over x plus 2 square plus 4 dx. Well, after I complete the square, you can see that I need 1 here, the one that I highlight in orange. I need number 1 there so I can integrate easily. So I'm going to pull out a quarter. So after I pull out a quarter, I hope that, well, it's going to be cleaner. So I pull out a quarter. So that means here I have x plus 2 square over 4 plus 1. Right? So I pull out number 4 there. So that's what I have. And then from x plus 2 square over 4, I can simplify more. So this is going to be x plus 2 over 2 square. Perfect. So what I have now is I have 1 over something that I highlight in light blue square plus 1. So I am going to make a substitution. So let u equal to x plus 2 over 2, right? And then if I define u to be this thing, so my integrand is going to be 1 over 4 times integrate 1 over 1 plus u square. Exactly, this is what we want, right? Because we know how to integrate this thing. And then because I do this substitution, so my dx is what? So I differentiate u with respect to x. So I get 1/2, which means my dx it's going to be 2 du. Sounds good? And then that means I can replace my dx by 2 du. Which is nice because I can cancel 2 and 4, so I get 1/2 here. And then I have integrate 1 over 1 plus u squared du. And it matches with the form I know how to integrate. So I have 1/2 times arctan u plus c. Well, my answer is 1/2 times arctan x plus 2 over 2 plus c. All right, this is how to integrate this question. Well, this is your first time that you have seen this thing. Well, remember this technique because we're going to use it again and again after midterm. When you see the denominator that you have something that you can complete the square, so you should complete the square and it's going to come back to arctan. This is the standard trick that we use a lot. All right, another standard trick that we can use is when we see cosine square and sine square. So we're going to illustrate that in example 64. All right, so let's look at example 64. So we want to evaluate the integral of cosine square root x over square root x dx. Well, this is considered as a medium one to hard one if it show up on the exam. What I am trying to show you now here, so for this question, I'm going to show you how to deal with sine square and cosine square. Well, this is going to be the technique that we're going to use all the time when we face sine square or cosine square. So let's look at it. So first of all, I see cosine square of square root x, right, over square root x here. So I feel it is, messy when you see square root x. So I want to make a substitution first. So I'm going to let my u to be square root x. Because I hope that if I make a substitution here, so something going to be better and I can cancel square root x on the denominator. So this is x to the 1/2. So when you differentiate u with respect to x, so you get 1/2 x to the negative 1/2. Well, if you simplify that, it's going to be 1 over 2 square root x, which means dx is equal to 2 square root x du. Sounds good, because if I start from the given problem, and then now I switch everything to u. So I'm going to have integrate cosine square u over square root x, right? And then I switch my dx to 2 square root x du. And then you can see that your square root x cancel. And then to integrate cosine square u du. Here is the problem. So how do we deal with integrate cosine square u du? So if you try to make a substitution, you will see that it is impossible to do a u substitution and integrate cosine square. So when you face the cosine square, remember that this is the trick. This is the trick that you have to use it all the time, even after midterm. So when you face cosine square or sine square, so we need to use identities. You have no choice. So for cosine square and sine square, so you have to use identity. So the identity that we're going to use is here. If I have cosine square of a, so this is going to be 1 plus cosine 2a over 2. This came from the double angle formula of cosine. And also sine square a, this is going to be 1 minus cosine 2a over 2. Well, you have no choice. When you face cosine square or sine square, this is the way you have to go. So what I'm gonna do is I'm gonna simplify this thing to, well, cosine square u, right? So I'm gonna change it to 1 plus cosine 2u over 2 du. Well, that's how we did it. And then we just cancel 2. And then after that, I have integrate. This is by identity. So, and then after that, I have integrate 1 plus cosine 2u du. And hopefully now you can integrate that. So it's going to be integrate 1 du plus integrate cosine 2u du. So integrate 1 du is going to be just u. So integrate cosine 2u du, you can say that this is, well, I'm going to switch my du to d to u and then over 2. So this thing is going to be 1/2 times sine 2u and then plus c. All right, I know I go fast on this thing, but hopefully you can follow that. So the idea of this is, for here, this term, if you feel like you have a hard time to follow me on this term, think of I do another substitution. So I can let v equal to 2u. And then I am trying to find dv equal to 2 du. So that means I can switch du to dv over 2, which is d2u over 2. So this is how we integrate, but we just make the form more compact so we can integrate faster. So after that, I can make u back to x. So I'm gonna get, because u is square root x, so this is square root x plus 1/2 sine 2 square root x plus c. All right, so this is the answer for this question. All right, so we start the first 15 minutes today by looking at 2 examples here. And I told you right now that these 2 examples are not easy. And I hope that you feel like, you should feel like integration is an art. So there's no standard way for every question for integration. It's going to be like using a technique to do that. Well, I have question from students. So can we use du and we multiply 2n divided 2? So I mean, if you cannot follow this question, you will talk to me later then, because I don't quite get what he asks. But well, integrate cosine to u du, you can make a substitution. Yeah, that's the key. All right, so let's skip example 63 and 64. So we're gonna learn this thing a lot after midterm when we talk about integral of trigonometric functions. All right, so let's move to another topic for today, which is going to be definite integrals. So today we hope that we're gonna learn definite integral and also the first fundamental theorem of calculus. All right. So let's look at definite integrals. So before we talk about definite integral, we are going to look at the related problems, which is the area under the curve. So let f be a continuous function on AB. So this is my function f that I highlight in light blue. So note, student name note, we'll talk later after class. So I got your question. Well, let's come back to this thing. Let f be a continuous function on AB. We will find the area under the curve here from A to B. So the area that I shaded here, this is what we want to find the area. So the idea of the definite integral is we are going to find the area from x equal to A to x equal to B. So the idea, we are going to split the interval AB into, split that into n pieces. Well, to make it easy, we are going to chop it into n pieces equally likely. That means I'm gonna say, hey, let's chop it to n pieces, and each pieces have the same length. So that means that one have the same length, right? So from A to x1, x1 to x2 have the same length. Let's do that first. And then to find the area under the curve, well, we can look at the y value at x1, the y value at x2, the y value at x3, and we trying to compute the area of the box, right? If we compute the area for each box, like each stack, and then we sum it together, we should get the approximate area under the curve. So what I just said can be summarized on this picture. So you can see that. So I have from A to B, right? And then I have the curve here. And then what I just did is from A to x1, I have the first interval here. So what I did is I look at the y value at x1. And then, well, I just make the box, use the y value at x1. When I draw the box here, I can find the area easily because the area of the box here is going to be, the height times the length. Well, done. Well, I know that I am going to miss some area because the area that I highlight in yellow is the one I missed. Fine. So next, we are going to look at x1 to x2. So we are going to, hey, let's look at x2. And then we look at the y value at x2. And then we make the box again. And then we can compute the area for this stack. For sure, this is not exact because we're going to miss something a little bit, sure. Well, you keep doing that for each stack. You can see that at some point, at some stack, you're going to have the area of the box that is greater than what you want to. For example, like from xi minus 1 to xi. This stack, you get the area that is over what you want, right? It is okay that you keep missing some area or getting over on some area, because at the end, we are going to take n go to infinity. So you can see here from the first picture to the second picture to the third picture, if I increase my n to infinity, what happened? So from the first picture, I only use 4 stacks. Well, the approximate area is not going to be good. I miss a lot of, the box is not going to be a good approximation because I missed this area, and then also I count the area that I highlight in light blue too. So the area is not exact, but after I use 8 stacks, so I make ends getting bigger. You can see clearly that the approximation is better, right? And also if I keep going, I do more stack, so you can see that, hey, it's getting better, and then at the end, when n go to infinity, your stack gonna be just the vertical line, and that is the area. This is the idea how we define definite integral, and this is called Riemann integral. So let's sum it up again. Well, so let's suppose that you have the curve that I highlight in orange. So what are we going to do now? We are going to just chop it into n pieces. So the x value from A to B here. So I'm gonna chop it into n pieces. And then for each pieces, so I'm gonna pick the point that is going to be the representation of that stack called xi star. So like for example, on the first stack, I call this point to be my representative for that stack. And then the second stack here from x1 to x2, I'm going to call this point to be my representative. No matter choice of xi star you pick, at the end, you're going to take n go to infinity. It's going to be just the line, the vertical line anyway. So it doesn't matter how you pick xi star. So if you keep doing that, you're going to get the area under the curve. Well, the approximation is going to be better again and again after you take limit when n go to infinity. So you can see that. Well, look at the one I highlight here. So x sub I minus x sub I minus 1. This is the length of the base of the stack. Fxi star, this is going to be the height of the stack. So you multiply it together, so you get the area of the stack. And then you have n pieces. So you summation from I equal to 1 to n. And then after that, you take limit when n go to infinity. Done. This is called Riemann sum, limit of Riemann sum. And we're going to give it a name, definite integral of f from a to b with this notation. So this is the real definition of definite integral. So integrate from a to b fx dx. If you want to find definite integral from a to b of fx dx, this is what people should do 200 years ago. So we are going to just draw the graph of f, right? Once you know the graph of f, so I want to integrate from a to b. Then I can chop this thing into n pieces. And then for each pieces, I'm gonna pick just the one point to be our representative. Maybe I am going to pick the midpoint. And then I draw the stack. I draw the stack. I draw the stack here, for example. I draw the stack here, for example. Well, this is going to be my approximation for this area under the curve. Well, and then I take limit when n go to infinity. So that is how we compute integral from a to b, fx dx. This is a real definition, but this is 2020. For now, we have we have a theorem, so we can deal with definite integral easily. We don't have to go back to definition all the time. This is definition. Well, when you learn calculus, it is good to know the real definition. But in practice, we are not going to use this definition because it is hard to use. For math people, yes, you should learn it because you want to learn some history, some background, how it develops. But for engineering students, we are not going to look at the theory in deeply. We're not going back to how to, going back to history or background, how people develop integration. So maybe in Wednesday, you are going to learn something called the fundamental theorem of calculus. And that thing going to help you to compute integral easily by using the fundamental. You don't have to draw the picture and compute the Riemann sum at all. All right, so let's stop here for the definition of definite integrals. We are going to look at the properties and some examples. So from definite integrals definition, we can show that if you integrate from a to a, so you get 0, which makes sense. Because if you integrate from A to A, so that's no area at all. So if you integrate from A to B, so you're gonna get what? This is typo. So this is yes, not typo. So you get A to B, so you can swap A to B to B to A, but you need the negative sign here. This is a good property too. And then the third one, if you integrate from A to B, and you know that you have a point C that is in between A and B, you can split it. Sounds good? So you can split it into A to C plus C to B. So we can use that thing to solve a little problem here. So let's say that I have integral from 1 to 4 of f equal to 5, integral from 3 to 4 of f equal to 2, integral from 1 to 8 of f equal to 11. Can you find A? I want integral from 4 to 8, fx dx. Well, because I know integral from 1 to 8 and integral from 1 to 4. Sounds good. That means I am going to say this is going to be my integral from 1 to 8. That means you compute the area of the area under the curve y equal to fx from x equal to 1 to x equal to 8. And then you subtract integral from 1 to 4 fx dx, which is going to give you back integral from 4 to 8, right? And that is 11 minus 5, which is 6. So easy and simple. So part B, you want to integrate 1 to 3 fx dx, right? You can see that this thing is integrate 1 to 4 fx dx. And then you minus integrate 3 to 4 fx dx, right? And then you're going to get back 1 to 3. And this is going to be 5 minus 2, which is 3. So basically, this slide told us that for integration, well, at least we can use this thing. We can split the lower bound and upper bound of the integration if we know the middle point between them. All right, so let's move to something more interesting. So let's look at example 65. This is going to be a good one to sum up your idea about the definition of definite integrals. So example 65, I want you to use the definite integrals. Find the value of this definite integral by using a geometric area. All right. So let's look at this thing. So I want to compute integrate negative 2 to square root x plus 1 dx. Well, if you think of geometry, this thing is going to be area under the curve y equal to square root x plus 1 from x equal to negative 2 to x equal to 2. This is by definition of definite integrals, right? Definite integral from a to b of fx dx. This is area under the curve. Well, I should say above the x-axis. Above the x-axis. Area under the curve y equal to fx above the x-axis from x equal to a to x equal to b. So if I want integrate from negative 2 to 2 of integrand absolute x plus 1 dx, that means I want to compute the area under the curve. Well, note that this is above the x-axis. from x equal to negative 2 to 2. So I'm gonna draw the picture y equal to square root x plus 1. All right, so my picture is going to be like that. So let's think about how to draw this picture. So what is the graph of y equal to absolute x plus 1? So for sure, the graph here is like a V shape, but because we have x plus 1 inside absolute value, it's gonna shift to the left by 1. So this is going to be my graph. All right, so that is my graph y equal to absolute x plus 1. And my vertex is going to be x equal to negative 1, y equal to 0. All right, so this is the same graph with y equal to absolute x, but shift to the left by 1 because I have x plus 1 inside the absolute value. And what I want is I want to compute the area under the curve from x equal to negative 2. This is x equal to negative 2 to x equal to 2. So this area under the curve above the x-axis, this is called the indefinite integral, right? So that means integrate from negative 2 to 2 of absolute x plus 1 dx. This is going to be the area number 1, which is here, plus the area number 2, which is here. So for the area number 1 that I just highlight in light blue here. So how do you compute it? This is the triangle. So this is going to be 1/2 times base times height. My base has length 1. My height has length, this is my base, has length 1. Right? My height, so when x equal to negative 2, y equal to, let's see, x equal to negative 2, y equal to negative 2 plus 1 is negative 1, y equal to 1. So this is 1. So that means this is the area that I highlight in light blue. This is 1/2. Well, what about the area that I highlight in yellow here? So that is going to be what? So let's look at that. So this is going to be 1/2 times base. Base here, this is 3, right? The length of 3. And then also the height here, this is 3, right? So that means 1/2 times 3 times 3. This is going to be 9/2. And then when you add them up, so you get 5. So this is your answer. Without using any absolute x plus 1 dx, this is equal to 5. Does it make sense? Any questions? Well, I know that some of you say that, Ajahn, it seems hard that we have to draw the picture and look at the area of the curve. Do we have another way? The answer is yes. Well, after we learn the fundamental theorem of calculus, we're gonna have the way to integrate this thing easily. The fundamental theorem of calculus is the one you learn in high school. The one that you integrate from A to B and then you compute antiderivative and then you plug in the antiderivative at B minus antiderivative at A. That thing is called the fundamental theorem of calculus, which we are going to learn, well, maybe on Wednesday or today. Depends on the time. But let's suppose that we don't know how to use the fundamental theorem of calculus. You need to use the geometry like this. Does it make sense? All right. Any questions before we move to the fundamental theorem of calculus? I think the next topic. So far, so good? All right. I hope you're still with me. All right. For those of you who are already in, so type check in, please. Well, some of you did already, but type check in, please, so I know you're here now. uh, for the remaining time, like about 40 minutes, so we are going to talk about the fundamental theory of calculus. And I think this topic is not hard, but it's supposed to be new for you. So please stay with me so you don't have to study this thing by yourself later if you listen to me now. All right, so ready? All right, 42 students here. Thank you everyone for showing up today. So we are going to look at the next topic. This is the important one. This is the fundamental theory of calculus. All right. So the fundamental theory of calculus, we have two parts, part 1 and part 2. All right. We have part 1 and part 2. So today, at least, we're gonna go over part 1. So part 1 is the one that we say that if we have differentiate of integral of constant to x of f t dt, it's gonna go back to fx. This is the fundamental theorem part 1. So the fundamental theorem part 2, this is going to be integral from a to b fx dx. This is going to be your antiderivative f at b minus antiderivative f at a. So I think about 40 students here, so you are more familiar with the fundamental theorem part 2. This is the one you use a lot in high school when you integrate, like, hey, Ajahn, I integrate x squared, so I get x cubed over 3. And then if I want to integrate from 1 to 2, so I'm going to plug in 2, plug in 1, and then subtract, and then done. You just use the fundamental theorem of calculus part 2. So we're going to learn that thing on Wednesday, I think. So today we are going to just look at the fundamental theorem part 1 first. So let's look at the statement. So the statement said that if you have f to be a continuous function from a to b, and you define your function g to be something like this, well, if you differentiate, I mean, you take the integral first of the function f from a to x, and then you differentiate after, well, you're gonna get back fx. So this means your differential operator and your integral operator, they are inverse of each other. So the good thing is that you don't have to differentiate that, you don't have to integrate that inside, because if you have differentiate attached with it, well, fine. So we are going to replace our x inside this thing and done. All right, are you ready for the example? Well, to be honest, I told you this topic is easy, but it just some of you skip this topic, and when you do the exam or homework or something, you spend a lot of time to trying to figure out how to integrate, but you forgot that you have d by dx attached with it. Well, we don't want you to integrate. We want you to use the fundamental theorem of calculus. So let's look at that. Okay, so let's look at example 66. This is supposed to be the easy one on the exam. Well, we used to test you on this thing. And you know what? So when you want to compute, let's look at the problem. So we want gx, we have gx integrate from 0 to x, the cube root of sine t dt. And then we want you to find the derivative of g. Some of you, if you don't know the idea of the fundamental theorem calculus at all, so you're gonna try to integrate this. And then you're gonna, hey, Ajahn, I cannot integrate this thing because this is so hard to integrate, right? This thing, well, can I pick u equal to sine t, and then I make a substitution, and then I'm trying so hard and I cannot integrate that. Well, because this is not supposed for the integration. So what we ask you is, we ask you to differentiate gx, which means I want you to differentiate integral from 0 to x, the cube root of psi t dt, which means, well, by the fundamental theorem of calculus, you have d by dx from 0 to x, this. So you can replace x inside the function here. So which means you're going to get cube root of psi x. That's it. That's it. Pretty simple like that. And then you get 2 points on the exam easily. So this is called the fundamental theorem of calculus. So what you have to memorize is d by dx of integrate any constant here, doesn't have to be 0, any constant here, integrate from constant to x, d by dx of the function ft dt. I get back fx. All right, memorize this. Memorize. All right. Well, you can see the reason why I use t here. I don't want you to get confused with x. So I switch my dummy variable from x to t here. So you can see, hey, I integrate from t to x, t from that constant to x. So that's, we use t because we want to avoid our confusion, because we're going to save x for something else. All right, so that is called the fundamental theorem of calculus. So let's talk more about the chain rule and fundamental theorem of calculus together. Let's say if you don't have x on the top here, well, on the upper bound of the integral, you have some function u. Well, the same thing, you can replace your ux here, but by the chain rule, you have to differentiate u and attach with it. So I'm going to show you example here. For example, I have fx equal to integrate from -1 to psi x, 1 over t cubed plus 2 dt. I want you to find f prime x. So how could I do it? Well, f prime x, this is going to be d by dx of integrate -1 psi x 1 over t cubed plus 2 dt, right? And then you can see that, well, I have the form that is almost matched with the fundamental theorem of calculus. The only thing I have a problem is psi x here, because for the fundamental theorem of calculus, it said that d by dx of integrate any constant to x ft dt, you get back fx, right? Well, here I don't have x on the top, but I have psi x. Well, easy, so I'm going to apply the chain rule here. So that will be my 1 over, well, instead of plug in t, I'm going to plug in psi x by the chain rule. And then I have to differentiate psi x one more time, because this is by the chain rule. And then at the end, I differentiate psi, I get cosine. That is my answer. Well, pretty simple, right? So I hope that the fundamental calculus is going to be your easy question on the exam. So everyone shouldn't miss this thing, because this is so simple and easy. But so many times students just skip this content. You're trying to focus on something else, and you forgot to study the first form of the fundamental theorem of calculus. So let's do one more. So I have here I differentiate f. So I get d by dx, integrate cube the fourth root of x to 10 cosine t to the fourth power dt. All right, for this thing, you can see that the form is not nice. because we have the constant on the upper bound, which we don't like it. We want the constant on the lower bound. So I am going to switch it first. So I'm going to switch it to, well, let's save the space here. So d by dx, I'm going to switch that to 10 to the cube root, the fourth root, sorry, of x cosine t to the fourth power dt. Well, if I switch number 10 and that cube root of x, the fourth root of x, so I need negative sign, right? I need negative sign because if I want to switch integral from a to b to b to a, so I need negative sign to swap it. Well, that's the property from the previous slide here, right? So if I want to switch from a to b to b to a, I need to add the negative sign there. So I'm going to use it here. So, all right. And then after that, I pull out the negative sign. So I have d by dx integrate 10 to the fourth root of x cosine t to the fourth power dt. So now I can apply the fundamental theorem of calculus with the chain rule. So I have negative and then cosine the fourth root of x. That is when I plug in the fourth root of x inside the function, right? And then not yet, so raised to the fourth power. So cosine t to the fourth power, so I just replace t by that fourth root of x. And then also by the chain rule, I need to differentiate x to the 1/4, right? And then I simplify a little bit, so I get negative cosine x because that cancel out. And then I differentiate that, so I get 1/4 x to the negative 3/4. Well, that's my answer. So if you want to simplify, this is going to be negative cosine x over 4x to the 3/4. All right. Not hard at all, but it just you have to be precise on theorem. If you know how to apply the first fundamental theorem of calculus, shouldn't be hard at all. All right, I think that I'm gonna continue this. I'm not going to give you a break because you know we can leave early as usual. So we're gonna move to example 68. Let me see. Okay, two more for the first fundamental theorem of calculus, and then we're gonna move to the second part, and then we're gonna stop at some point at about 4:15 to 4:20. We're gonna stop today. So let's look at example 68, another one. Well, this is an interesting one. This is the O exam. Well, this is the same difficulty that you're gonna see on the exam. Same difficulty that you're gonna see on the exam for the medium to hard one. So I want you to evaluate, integrate from x to x cube 1/t cube plus 7 dt. You know, some student gonna integrate first and then differentiate after, which is stupid. Because if you are trying to integrate that, how could you do it? No way. No way you can integrate 1/3 cube plus 7 over dt. If you try to pick u equal to that, not work. Well, this is one of the hardest integrate that you're gonna have for this class, right? Because, well, even you learn integration by part or something after midterm, this integrand is still super hard to integrate. So, because you see that you have this d by dx with the integration, this is a question that asks you about the fundamental theorem of calculus for sure. So what are we going to do is, well, because the fundamental theorem say that d by dx of integrate constant to x here of ft dt equal to fx. Keep that in mind because you have this thing all the time. Well, you need constant for the lower bound. So what I'm going to do first is, well, because I need constant on the lower bound, why don't I split x to 2x cubed to something first? So I'm going to split that from x to 2x cubed from x to 0, 1 over t cubed plus 7 dt. And then plus 0 to 2x cubed, 1 over t cubed plus 7 dt. This is acceptable because you know that integrate from a to c, right? This is integrate from a to b plus integrate from b to c. You can pick b, whatever you want. Well, if you say that, Ajahn, why did you pick number 0? Well, if you don't like it, you can pick number 20. If you don't like it, you can pick number 20. Whatever you want. If I don't like it, I can pick 20. Oh, okay. This is too small. Maybe I can pick like 1 times 10 to the negative 7 or whatever. You can pick the number here, but it doesn't matter to our integral. So after that, let's say that we are going to pick number 20. So this can be any number. So after that, we are going to split it into 2 pieces. So this is integrate from x to 2020. All right, and then plus d by dx. So what I did here, I expand the differential operator. So I can do 2 pieces separately. All right. Well, this form looks good at least because you have the constant in the bottom. But the first form doesn't look good to me because I have the constant on the top. So I'm going to switch one more time. So it's going to be negative d by dx integrate 2020 to x 1 over t cubed plus 7 dt. Well, the negative sign comes from the action that I switch 20 and x. And then on the second term here, well, I will differentiate later. So just copy that first. All right, now we are ready to use the fundamental theorem of calculus. So for the first term, I'm gonna get negative 1 over x cubed plus 7, right? Because I already have constant to x, right? So good. The second term I am going to have plus 1 over 2x cubed plus 7. However, because this is not just x, so I need to differentiate 2x cubed again. So I get 3x squared. No, not 3. 6x squared. Right? Because I differentiate 2x cubed, so I get 6x squared. Well, if you simplify everything, so you're going to get negative 1 over x cubed plus 7 plus 6x squared over 8x to the 9 power plus 7. Well, this is our answer. Without doing any integration, easy, right? Just use the fundamental theorem of calculus. Siropop said y is the first term negative. Yes, and thank you, Puin and Supuit, because we swap the bound, right? Because this is x to 2020, right? So we want to swap it to 2020 to x. So I told you that if I want to integrate from a to b, this is equal to negative integrate from b to a. So you can swap the lower bound and upper bound, but you need to add negative sign there. All right. Well, this is considered as a medium to hard one on the exam, and hopefully you can do this one for this year. All right, so let's do one more, and then we just going to stop the first part of fundamental theorem of calculus. All right, so example 69. All right, so this is also the O exam. but not for engineering students. I copy this thing from science students. Well, but it's still a good problem practice. So let's look at the example 69. I want you to find f prime 0. This is my notation. So f prime 0 when the function f is given. Well, let's do that. This is pretty simple. It's similar to the last one. So you have fx here, which is integrate x squared to arctan x sine 3 minus square root t plus 1 dt. Well, I'm going to differentiate that, right? And then, as shown before, we should split it into two pieces. So I'm going to do, because here we have x squared to arctan, right? So I'm going to integrate x squared to 0 first. And then I am going to integrate 0 to arctan x. Sounds good? Because I split it using 0 as our midpoint between them. And then after that, I swap x squared and 0. So I'm going to say, hey, this is my 0 here. This is my x squared here. And then I add negative sign. You can see I did something so fast, right? So I swap it and then negative sign. All right. So I'm going to copy that. Then paste smart. All right. And then that. So I'm going to minus that. Then 0 to x squared. Good. And then now we are ready. So we are going to apply the fundamental theorem of calculus. So this is negative. All right. So the first term, sine 3 minus square root t plus 1. Well, our t now is x squared plus 1. And then differentiate to x. So you get, or differentiate x squared, you get 2x, sorry. Right, this thing from the chain rule, right? And then on the second term, I have sine 3 minus square root arctan x minus 1. And then I differentiate arctan, so I get 1 over 1 plus x squared. All right. Easy. And then after that, I plug in 0. So every time when you are asked to compute the derivative, at some point, compute the derivative first and then plug in the value after. Well, some of you asked me, is it possible to plug in 0 first and then differentiate? The answer is no. Otherwise, you get 0 all the time, right? Because if you plug in the number first, I mean, plug in the x value first, so you get constant, and then you differentiate, you get 0 all the time. That is not acceptable. So the correct way is you find derivative first, and then you plug in 0 after. So I'm gonna plug in that.
Excuse me, how ajan?
Oh, arctan x plus 1, right? Someone said that.
Excuse me, a question.
Go for it.
So when we do the chain rule, is it for the integral or is it just the x squared plus 1 inside, or is it just x squared only?
Okay, when we do the chain rule, this is for, well, let me highlight this. You look at the first term here. When I do the chain rule for the first term, well, I have x squared here. So I do the chain rule for x squared get to x. You do not need to touch sign something in the integrand. Don't touch it. And then the second term here, I have d by dx integrate from some constant to arctan x. So I'm gonna just replace arctan x into my integrand. and then I differentiate arctan x. No need to integrate sine or anything on the integrand. Make sense?
ขอบคุณครับ
Okay, next we are going to compute this thing. So when you compute that, take a look. When you plug in 0, you plug in x equal to 0 here. So that term gonna be 0. Don't think too much, right? Because you plug in 0, so the first term is 0. And then you plug in 0 that, so you're gonna get that. Well, this term you have to be careful, right? Because this is not 0. And then 1 over 1 plus 0 square. All right? You cannot leave the answer like that. This is unacceptable because you know how to get the arctan 0. What is arctan 0? So the arctan 0 is the angle that when you take the tan, you get back 0, right? So what tan, you tan of what angle you get 0, it's going to be 0, right? So that means you get 0 plus sine of 3 minus 1 times 1, which is, this is the answer, is sine 2. Well, again, when we talk about trigonometric functions, we talk about radians. The unit gonna be radian, not degree. Make sense? Because radian is just much simpler for math people. So we're gonna use radian here. So sine 2, this is not sine 2 degrees, it means sine 2 radian. All right, so arctan 0, this is the 0 because tan 0 is equal to 0. All right, so that is the end of the first fundamental theorem of calculus. Well, I think we have time. So let me go 10 more minutes and then I will stop. So we're gonna talk about fundamental theorem part 2 and do maybe 1 or 2 examples, the little one, so we can stop. All right. So let's do that. So let's do part 2. This is the one that you are familiar. Because in the high school, you, well, I mean, if you learn AP calculus or something before, or if you learn calculus from anywhere, so it's, you have seen this thing before. So this is the one that when people learn calculus for the first time, you're gonna think that this is your formula. It is not a formula. This is a theorem. This is a theorem. This is a big theorem. This is a theorem that changed the world. Because before, when you compute integral from a to b fx dx, before, if you don't have this theorem, you have to compute this thing by, hey, we have to pick xi star, and then we have to pick xi minus 1, and then we compute the Riemann sum, and then we take limit. And then you're gonna say, what the heck is this thing? This is so tedious. People try to find a way to avoid this thing because this Riemann sum is so hard to deal with, because you have to compute the summation first, and then you take limit after. It's gonna be so many, you know, it's time consuming. So in about, I think, late 18th century or something like that, if I'm not wrong, so mathematician, we developed the theorem, and finally we hit the fundamental theorem of calculus, which is this thing. Well, by the name, you can see that this is fundamental, which is super important. This is the basic theorem for calculus. So it states that if you have integrate from a to b fx dx, you don't have to go by using Riemann sum. You can find the antiderivative, capital F, and then you just evaluate antiderivative at b minus antiderivative at a. You know, it's make the world a lot easier because we know how to find antiderivative. And then it just plug in b and a, add antiderivative, and then done. So this is the step, right? Integrate fx dx, and then so you obtain the antiderivative first, and then you evaluate at b minus evaluate at a. Well, thank you for, you know, I don't know who did this, Newton or something, Sir Isaac Newton or something, who just proved this thing, and then we have that, and then it saves our time to compute definite integrals. So you're gonna see the power of this thing in a minute. So let's look at the basic example here. So when we have integrate cosine x dx, well, I don't have to go by Riemann sum. I mean, if I want to use Riemann sum, I have to draw the graph, cosine, which is that. Well, let's suppose that I don't have the fundamental theorem of calculus. I need to draw cosine, and then I just need to, hey, 0 to pi over 4 is what? It's this, right? 0 to pi over 4. And then, oh my God, I need to, from 0 to 4, I have to chop into n pieces. And then I have to find the area under the curve by the Riemann sum. And then after that, I take limit when n go to infinity. Well, it's gonna take you maybe about 15 to 20 minutes to get the integral of this thing without using the fundamental theorem of calculus. But now we are smarter than that. That is the people in the the ancient world. So we are going. Any question? Okay, go for it.
Is there going to be the Riemann sum in the exam?
Oh, okay. On the Riemann sum, I just taught you because I want to teach you, but on the exam, we are not going to ask you to do the Riemann sum.
Oh, okay.
So Riemann sum is not included on the exam. Sounds good? Well, but you need to learn it because this is the the idea of the calculus. Yeah, but on the exam, we're gonna start from using geometry to compute the integral. The example that I showed you, the absolute thing, that could be the one problem on the exam, but for the Riemann sum, we're not going to ask you on that thing. So I'm gonna review you again when the chapter is over. All right, so let's do this page and then we can go. So let's do 70 and we're gonna come back on 71 on Wednesday. So let's do 70 very quick. So 5 minutes here. So let's do integral from cosine x dx from 0 to pi over 4. Hey, this is super easy. I like it, right? Because this is, well, now you can integrate cosine, so you get sine. Wow, simple. And then you evaluate at x equal to pi over 4 minus x equal to 4. Woo! Sine pi over 4 minus sine 0. And then that is square root 2 over 2, right? Or 1 over square root 2, doesn't matter. Minus 0, so you get square root 2 over 2. OMG, right? You got it in a minute, very quick, less than a minute, because you know the entirety of cosine, and that's it. All right, so the geometric meaning, this is the area under the curve, y equal to cosine x from 0 to pi over 4. That is the geometric meaning of this thing. All right, so the last question for today, integrate 2x plus 1 over square root 1 minus x squared. So think of this thing. So it must be some form that you know how to integrate. You have the formula of this thing, right? If you want to remember. So this is similar to the formula of arc sine. All right, so we're going to integrate that. So integrate 2x. So I do not need to integrate 2. And then I integrate x. If you remember when we compute the antiderivative of x, so I get x squared over 2, right? And then after that, look at my notation. When I write the differentiation here, I usually use bracket here, right? And then I do the vertical line to state that, hey, I'm ready to evaluate at b minus a. All right, and then plus I integrate that thing. Whoa, that thing is arc sine. All right, and then I evaluate x equal to 1/2 minus x equal to 0. And then after that here, I cancel 2 first. So I plug in 1/2 square and then plus arc sine 1/2. And then minus. So I like 0 so much because when you plug in 0, everything gonna be easy. All right. Well, let's compute this thing. So that thing is 1/4. What is arc sine 1/2? So for arc sine 1/2, for those of you who are not expert in trigonometry, arc sine 1/2 mean you need the angle that you take sine theta and then you get back 1/2. Of course, there's so many angles that you're gonna take sine and come back to 1/2. So we have to pick the one in the interval from negative pi over 2 to pi over 2, right? This is the domain for inverse trigonometric function, inverse sine function. So that means we have to pick pi over 6, right? Let's say if I want arc sine negative 1/2 here, so I am going to get negative pi over 6 because I need to pick the angle in this domain, right? This is from your inverse trigonometric function. This is from your pre-calculus, your basic one. And then after that here, so I have 0 and arc sine 0 is 0. Well, the answer is going to be just 1/4 plus pi over 6. Good. All right. That is all for today. All right. So on Wednesday, we're going to just come back and do harder example, getting harder. We have few example left, I think, about 5 example left. So we're going to come back and finish it all on Wednesday, and we're going to talk about chapter 4. All right, which is the last chapter for midterm, which is good. If we finish early, I can keep doing a practice problem for you. That will be your preparation for midterm as well. Any question for today? Anything else? Well, if you don't have any question, you can leave now. So for those of you who have question, I am going to stay here with you for 5 to 10 minutes more. Okay, thank you for attending today.